Hello everyone, and welcome to week 10 of Poll 361. This week we're going to continue to build upon the things that we learned last week, specifically regarding the normal distribution and standard deviations. In this lecture, we're going to overview the characteristics of the normal distribution, discuss the statistical properties of the standard deviation in a little bit more detail, and then we're going to learn about z-scores and curve-tail probabilities, which will be instrumental in helping you learn how to test hypotheses and state how confident you are that there is in fact a relationship between a set of variables. And in this lecture, we are also going to work through some examples with z-scores so you understand how those relationships work. So last week, we spent a lot of time learning about and getting familiar with the normal distribution. So the normal distribution is special for a lot of reasons, but there are three specific characteristics of the normal distribution that I would like you to keep in mind. First, the y-axis on the normal distribution represents the probability of observing a specific value. Second, the center of the normal distribution represents the mean, median, and mode and has a value of 0. And third, the x-axis of the normal distribution is measured in standard deviations and represents the amount of dispersion within the data. So altogether, the normal distribution represents a way of standardizing data so we can make inferences not only about one set of observations, but many different variables or observations among a variety of different samples collected at different points in time. Standardization refers to the process of converting lots of different variables with different measurements like ordinal, ratio, and dichotomous levels of measurement all onto the same universal scale. So one example of standardizing data is by calculating the standard deviation in order to make inferences about whether data is clustered around the mean or whether observations have a high degree of variance. As you'll recall from last week, we discussed how you can make simple inferences about the size of the standard deviation simply by looking at the peaks of the normal distributions. So in this figure here, we can see that as the standard deviation increases, that the peaks of the data begin to flatten and widen. When the standard deviation is very low, that tells us that the observations do not deviate very much from the mean, just as the name suggests. And as the standard deviation gets bigger, that's telling us that the observations deviate a lot from the mean. In other words, there's a great amount of variance. Another critical component of standard deviations is that they can tell us a lot of information about what percentage of observations lie around the mean. So let's refresh with a quick recap. In the standardized normal distribution, the mean, median, and mode lie at the center, here. The bulk of observations lie between one standard deviation above and below the mean. And as we move further away from the mean, we notice that less and less observations fall within the tails of the distribution. And lastly, the normal distribution is perfectly symmetrical, meaning that 50% of observations are above the mean, median, and mode, and 50% of observations are below the mean, median, and mode. Now, before we continue, I do want to go over one quick example just to make sure that we understand what the normal distribution is telling us. Measuring the height of a sample of individuals is a common example used to illustrate the meaning of the normal distribution and the standard deviations. So as we've discussed at length throughout the course, it would be impossible to measure the height of every single American adult, and therefore the true population parameters are unknown. However, we can sample a group of individuals and try to make inferences about height. Now, say we measured the height of 100 American men. And as you can imagine, most men would have very similar heights on average. In other words, the height of most people would not deviate much from the mean. And this is a phenomenon that you see with almost all naturally occurring events. They tend to fall to this normal distribution curve. And if we surveyed enough people, we would likely come across a few people who were very, very tall. In other words, their height would deviate much higher than the mean. And we would also likely come across some individuals who were very, very short. In other words, their height deviated much lower from the mean. The point of the matter is recognizing that the probability of being very, very short or very, very tall is quite small. In fact, rarely do we see men who are 5 feet 2 inches in height, and it is similarly rare that we see men who are taller than 6 feet and 6 inches. So this is how we interpret the normal distribution. Now that you understand how to read a normal distribution, we can get into the specifics of the standard deviations. We know that the bulk of observations are clustered around the mean in the normal distribution, but what percentage of observations? That's where the standard deviation comes in. Now, approximately 34.1% of observations lie within one positive and one negative standard deviation from the mean. So you might be thinking to yourself, why 34.1% exactly? And answering that question involves a lot of calculus that you probably wouldn't care to be bothered with, but if you are really interested in learning more about this, there is a YouTube video in the weekly module that covers the central limit theorem, and it explains why each standard deviation constitutes a specific percentage of observations. Now, for the purposes of this course, I'm not super concerned that you understand the nuances of why X% is within each standard deviation away from the mean, but what are the main takeaways? Well, this means that a total of 68% of observations exist within one positive and negative deviation of the mean, because 34 plus 34 equals 68. And as we have already discussed, as we move further and further away from the mean, we see less and less observations. And that's why the percentage of observations in each subsequent standard deviation gets smaller. And this is because, as we have already noted, most of the observations are already accounted for within the close proximity to the mean. So about 13.6% of observations occur within 2 standard deviations above and below the mean, respectively. 2.1% of observations occur with 3 standard deviations above and below the mean. And finally, about 0.1% of observations occur within 4 standard deviations above and below the mean. So now that you understand how to interpret the normal distribution, standard deviations, and the percentage of observations that exist within each standard deviation, we can make some really cool statistical inferences with z-scores. Z-scores are just multiples of the standard deviation. If we had a z-score of positive 2, that means the same exact thing as a standard deviation of plus 2. A z-score of negative 1.5 would simply mean 1.5 standard deviations below the mean. So z-scores are just multiples of the standard deviation. And what's great about z-scores is that we can use them to calculate a ton of really useful information, such as what percentage of observations lie between one specific observation and the mean. Now, z-scores are reported in proportions, and they're telling us the probability that a score will fall in a specific range that we specify. So throughout this lecture, I'm going to be using percentages and proportions kind of interchangeably, but you can use whichever one you prefer. Whatever just makes the math stick best for you is the one that I'd like you to use. We can also tell what percentage or proportion of observations lie between 2 specific observations, or what percentage of observations exist above or below a specific observation or threshold. So how do we calculate z-scores? Well, there's 3 specific steps involved with the calculation, estimation, and application of z-scores. So the first thing that we have to do, obviously, is calculate the z-score with the z-score equation, which I will show you on the next slide. Second, we have to find the critical value of your z-score in the normal curve probabilities table. And this is going to tell you what percentage of observations fall between your score of interest and the mean. And then finally, we use those critical values to make a variety of assessments about the data. So all of this is pretty abstract, so let's just go ahead and start with breaking these things down and do some examples. So the first thing that you need to know is the equation for calculating a z-score, and it's super simple. Here you can see that z equals your score of interest minus the mean divided by the standard deviation. And we're going to do a ton of examples, not only in this lecture, but also in class. So we're going to get a lot of practice calculating z-scores because, again, this is the kind of basic, fundamental statistical analysis that really is the heart of more advanced statistical inferences that you will make. So like we said last week, right? Standard deviations are really important because they're going to be a component of all of our other equations that we learn. And here's our first example of that, having to know what the standard deviation is in order to calculate z-scores. Another way of writing the z-score equation in the mathematical symbols that I've been showing you guys is y, which is the score of interest, minus y bar, which is the sample mean. We've already talked about y bar quite a lot, divided by sigma hat. And sigma, as we know, is the standard deviation, and it has a hat because we put hats on Greek letters when they refer to samples. And if we were referring to the population, there would be no hat. So just keep in mind that hat refers to an estimation for a sample. Once you've obtained your z-score, you will then use the normal curve probabilities table to obtain a critical value. And again, this will tell you what percentage of observations lie between your score of interest and the mean. So here's the table that's provided to you in the Canvas module, and you'll notice it only includes positive values, but remember, the normal distribution is perfectly symmetrical. So the critical value of a positive z-score is exactly the same as a negative z-score. Once you've obtained your critical value, represented by all of the numbers here, then you can make inferences about your data. So I know that this might look a little overwhelming, so let's just jump right into an example to see how z-scores work. Example number 1. After the midterm exam, Professor Xavier reveals that the average exam score was a 77 with a standard deviation of 8. Rogue scored an 87 on the exam and wants to know what percentage of students scored below her and above her. Z-scores can help us answer this question. So the first step, we have to calculate the z-score. We know, as we just learned a few slides ago, the z-score is calculated by the score of interest minus the mean divided by the standard deviation. And all of that information was provided to us in the previous example. So we know that Rogue scored an 87. That is our score of interest. We are going to subtract the mean from that score of interest, which is 77, and then we're going to divide the standard deviation, which is 8. So 87 minus 77 equals 10. 10 divided by 8 equals 1.25. So this is our z-score, 1.25. Now that we've calculated our z-score, we have to go find the critical value in the curve probabilities table. So our z-score equals 1.25. Now we have to look it up in our table. And there are a ton of values in this table, so it's laid out in kind of a strange way, but all you need to know is that we look in this first column here that says z, and we want to identify the first two integers from our z-score. And there's a whole page of numbers on this PDF, but I'm just kind of showing you the top so we have enough room to see the numbers and know what we're working with. And we'll do more examples in class with larger z-scores. But here I'm going to show you how exactly we read the z-score table. So we know our z-score is 1.25. We have to find those first two integers in the leftmost column. So we can scroll all the way down and we see we've got 1.2. So those are the first two integers of our z-score because it's 1.25. And now we have to go all the way along this row until we get to the third integer of our z-score, which is 0.05 because the z-score is 1.25. So we've already got 1.2 here. Now we have to find the 5. and we circle this value right here, 0.3944. All you need to do is make sure that the first two integers line up in the first column, and then find that third integer along the row. We will do more examples if this is a little bit unclear. So now we have our critical value, which is 0.3944. And remember, this is telling us the percentage of observations between the mean and our score of interest. So how do we make inferences about who scored higher than Rogue or who scored lower than Rogue? Well, for these type of examples, I think it's always best to shade the normal distribution between your points in order to make your inferences, just like we did in class last week with the standard deviation examples. So here's our normal distribution, and we're going to color this in to help make sense of our observations. So it's always a good idea, like in your homework journals, to write out all of the information around the standard around the normal distribution so you know what your values are. So here I've just reported all of that same information. We know the mean is 77, the score of interest is 87, the z-score is 1.25, and the critical value is 0.3944. So the first thing I always like to do is to make a dot of where the z-score is on your normal distribution. So again, remember, z-scores are just multiples of the standard deviation. So since our z-score is 1.25, we're just going to put our dot here indicating the z-score at about 1.25 standard deviations. It's very important to remember that this is a positive value, so that's going to go to the right of the mean. Now we can incorporate our critical value within the bounds of the mean and our z-score. So remember, the critical value that we look up in the table, that tells us what percentage of observations lie between the mean and our score of interest. So since our critical value is 0.3944, we could simply move the decimal place twice, and we would have a percentage. So this critical value is telling us that approximately 39.44% of students scored between the mean, which was 77, and the score that Rogue made, which was 87. So about 39% of students fall in between the mean and Rogue's score. So this is a really important point. Don't forget, the critical value only tells you the distance between the score of interest and the mean. And remember, Rogue wanted to know the total number of people she scored higher than and the total number of people that scored above her. So for now, we can make the baseline inference that approximately 39.44% of students scored between the mean, 77, and Rogue's 87. But now let's try to answer the questions presented in the prompt. As we noted at the beginning of the lecture, the normal distribution is perfectly symmetrical, and that means that 50% of observations fall below the mean, median, and mode, and 50% of observations are above the mean, median, and mode. And again, I've just reported these as proportions because the z-scores and the critical values are also presented as proportions. So again, you're going to hear me kind of simultaneously use percentages and proportions, so I just don't want anybody to get confused by that. But we've got 50% on one side, 50% on the other side. So Rogue wanted to know what percentage of students she scored higher than. And so now we just have to fill in the information that we already have and kind of do some reverse engineering to answer the question. Lucky for us, we already know that 39% of students scored between the 77 and Rogue's 87. And the great thing about the normal distribution is that we know that 50% of observations lie beneath the mean. So hopefully you can see where we're going here. All we have to do is add 50, which is, 50% below the mean. And then we have to add that percentage between the mean and then Rogue's positive score, which was above the mean. So all we're doing is adding 50 plus 39.44, and then we get 89.44%. So this is telling us that Rogue scored higher than 89.44% of students. And finally, since we also know that the normal distribution accounts for 100% of observations, all we have to do is subtract what we already know from 100, because that's going to tell us what percentage of observations exist in this tail highlighted by yellow. So we take 100, we subtract what we already know, which is 89.44, and that equals 10.56. So, therefore, we know that only 10.56% of students scored higher than Rogue on the midterm exam. And if you ever want to double check your work, all you have to do is just add up these proportions. And if you've done everything correctly, they should sum to positive 1.00. Alternatively, if you're moving the decimal and calculating everything as a percentage, I'm happy with either. It should all sum up to 100. So it's up to you in your homework journals whether you use proportions or percentages. Just try to be consistent. And I hope all that makes sense. As long as you complete each of these steps methodically and you don't rush, you should end up with the correct answer. Again, we're not doing a whole lot of seriously complicated mathematics here. Let's run through one more example for the lecture using negative z-scores so you can understand how to use the curve probabilities table. Okay, so we're going to stay with the same example with the midterm with the average of 77 and the standard deviation of 8. But now we're going to throw another score of interest in. So we know that Rogue scored an 87, and now we're incorporating a new student, Scott, who scored a 73. So now we want to answer a new set of questions. Some of these are going to be recap, and another one's going to be something that we haven't yet done before. So we're going to answer what percentage of students scored below Scott, what percentage scored above Scott, and then here's our new question. What percentage scored between Scott and Rogue? And after some practice, you'll be able to just dive right into these problems and calculate all of the values that you'll need to answer any potential inference questions associated with z-scores. So we just jump right in. We know our score of interest is 73. We're going to subtract the mean from that, and as you can tell, we're going to get a negative integer here. So 73 minus 77 equals negative 4. We divide that by 8 because 8 is the standard deviation, and that equals negative 0.50. So now we look that up in our chart here. So we start with the first column and we identify the first two integers, which is 0.5. So we scroll down, we identify it here, 0.5. And since it's an even number, 0.50, we see that this corresponds with the very first column. And that gives us a critical value of 0.1915. So that is our critical value. Now we can throw up our normal distribution and start shading everything in and making sure that we understand how Scott's score compares to all of the other students who took the midterm exam. So again, I've put the information right up here. Mean equals 77. The score of interest is now 73, which is below the mean. The z-score is negative 0.5, and the critical value is 19.1915. So now that our z-score is negative, the first thing that you have to determine is if we're going to put our z-score dot to the left of the mean or to the right of the mean. So hopefully you were able to guess that since our z-score is negative 0.5, that means that our z-score dot is going to go right in between 0 and the negative 1 standard deviation, because this z-score is essentially half of one negative standard deviation. So our dot goes right here, and this represents where Scott's midterm exam score falls on the normal distribution. So the next thing we want to do is shade in that area between the mean and the score of interest. And remember, that associates with our critical value that we looked up in the table, 0.1915. So what this is telling us is I want you to think a little bit about it and see if you can try to summarize the significance of this statistic really quickly. But what this is telling us is that about 19.15% of students scored between the mean, which was 77, and Scott's 73. But we wanted to know what percentage of students scored below Scott. And since we know the critical value and we know that 50% of observations lie on either side of the mean, all we have to do is some really simple subtraction. So we take 50 or 0.5000, whichever you prefer. We take 50 and then we subtract that critical value, 19.15, and then that equals 30.85%, right? So basically all you have to do is make sure that each side of the distribution, whichever one you're on, that you're just making sure that they add up to 50, and you'll be able to do all of your inferences that way. So now we can see that 30.85% scored lower than Scott. But we also want to know what percentage scored higher than Scott. And again, as you get more experience and practice doing this, it's all just going to come together really quickly for you in your mind. So we know that, again, 50% of observations are to the right of the mean, but we know that Scott is also lagging behind. His score is under the mean. So all we have to do is add that critical value space again, 0.1915, and then add that to the 50% of observations that are to the right of the mean, and then we end up with 69.15. So you can just kind of follow along the arrow, and this means that 69.15% of students scored higher than Scott. I know we might be moving a little bit quickly, and you might kind of be struggling to fully conceptualize what it is that we're doing here. So if that is the case, I would just recommend you go back to the beginning of the examples, maybe watch it one or two more times, and just come to class on Thursday ready to do some more examples, because I promise you it will make more sense the more you do this. You just have to practice. So let's not forget that the very final question here was what percentage scored between Rogue and Scott? And we already did all of the work for that question, so really what we're going to be doing is just adding those two critical values together. Let's go ahead and mark it on our normal distribution what Rogue's z-score was, which was 1.25. We already found the critical value for that, which was 0.3944. And so all we have to do is add together the critical values of these shaded regions, and then we can completely understand the percentage of students that scored between these 2 points. So 0.1915 plus 0.3944, that equals 0.5859. So we could move that decimal to make it into a percentage, and we know that 58.59% of students scored between Scott's 73 and Rogue's 87. So I hope you found those examples helpful. Again, we will do a lot more in class to really make sure that you completely understand these processes. But just to do a quick recap, z-scores are simply multiples of the standard deviation. A z-score of 2 is the same exact thing as 2 positive standard deviations away from the mean. And z-scores allow us to make a variety of inferences, such as the percentage of observations between scores of interest and the mean, the percentage of observations between scores of interest, so maybe 2 or even 3 scores of interest. We could calculate all of the variance between those, the percentage of observations below or above a score of interest. The primary thing worth noting here is that z-scores allow us to standardize all of our variables and calculate relationships between those values. And finally, standardization also allows for the comparison of observations between different samples, even across different times. So z-scores are really the heart of statistical analysis. They will continue to guide our discussion next week when we get into hypothesis testing and setting critical values for alpha and things like that, which are the heart of the amount of confidence we have that 2 variables are in fact related. So that's all that I have this week for you guys. I hope you enjoyed, and I will see you guys on Thursday.